Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera again. So today is going to be our third meeting. So in today meeting we like to continue discussing about our week number 1 objective, which is, as we know, based on our course information, we are doing mathematical preliminaries, so revision on vectors, which I have done in my second lecture or second meeting. And today discussion we're going to focus on orthogonal coordinate system and vector calculus. So that's going to be our today meeting. Okay. So when we talk about orthogonal coordinate system, okay, so we can divide them into three types. Okay, the first one, which is common to us, we call it to be Cartesian coordinate. The second type of system that we going to use throughout the course, we call it to be cylindrical coordinate system. And finally, the third type that we're going to discuss will be spherical coordinate system. Okay, the reason why we have to learn all these three types, because in real engineering application, the dimension of problem that we dealt with not uniform, meaning that it's not flat. It can be other structure. For example, let's say we have a cable. Okay, a cable as shown here. So this cable, if you want to determine, for example, the electric field intensity generated by the cable, okay, so it's quite cumbersome and tedious if we use Cartesian, meaning that mathematically it's a bit tedious, long, lengthy, and cumbersome. So the best way to simplify the mathematical approach is by adopting the most possible shape how the field generated. From this simple structure, we can see the field coming out from this cable going to have a cylindrical shape. Therefore, it's much simpler if we adopt cylindrical coordinate for this particular problem rather than we use Cartesian. So that's the logical way why we have to learn various coordinate systems. So the reason is simple, just to simplify the mathematical approach when we have to calculate certain properties, engineering properties in that particular problem. Okay, so that's the reason why we have to learn all these different type coordinate system to simplify the problem solving. Okay, so what I'm going to go now, I'm going to talk about this coordinate system one by one. Okay, so what we're going to do now, we're going to try to fill in, okay, the informations needed to be filled in this table, and this table has been given to you all through handout number 2. So what this table is the summary of all the differential, length, surface, and volume regarding Cartesian coordinate, cylindrical coordinate, as well as spherical. So we need to fill all this form because this information very crucial for us to be used later on when we want to solve our EMT problem. Okay, that should be the second objective, to fill in the blank in that table. Okay, so let's go first type of coordinate system here. So Cartesian, which is the most common type coordinate system that we actually used. Okay, let's say we have a point P. So the point P is the way we define the position in space based on Cartesian. So the point P, if we are using Cartesian, going to have three variables, which known as x, y, and z. Okay, So now let's draw the actual diagram of this point P. So I'm going to draw it. Okay, we're going to have 3 axes. Okay, so this first axis we call it to be x-axis, y-axis, and z-axis. Okay, our point P, let's say located here. So this is our point P. Okay, we can represent point P in terms of vector. Let's say we want to show a vector from O to P. So we call it a position vector, vector OP. And from our previous discussion, that can be presented as x, and then in x directions, plus y, in y directions, plus z in z directions. Okay? And the way we're going to define this unit vector, okay, this we call it unit vector. So it's going to be the direction parallel to the given axis. For example, for unit vector x, it's going to be parallel to the x-axis. And for y, we're going to draw it to be parallel to the y-axis. And for the z, should be parallel to the... So that's how we draw the unit vector. Orthogonal meaning that all these unit vector having angle 90 degrees to each other. So that's what we call it, orthogonal coordinate system. Okay, that's very simple. So that's how we show a position in space using Cartesian coordinate system, okay, in terms of the position vector. So the issue now, when we talk about field, usually field never remains stationary in space. Okay, field always move. So meaning that what we're going to discuss now, what happened to this point P if moved to another position. Let's make it very close and give it to be P dash. So what happened when this point P shifted to the point P dash? So this is what our concern now. So what will that contribute when the point P now shifted to point? Because why we are thinking this way? Because the field, as we know, always propagate from point to point. So meaning that move. So we want to represent the movement now properly using what we call it to be using calculus. Okay, so that's what we're going to introduce now. When the point P move to point P, so three things will have three parameters were going to be affected. First, it's going to affect what we call it the length factor. The second parameter that's going to be affected going to be what we call it to be surface around the movement of point P to P point or P to P prime. And the third parameter that's going to affect it is the volume whereby the point P is shifted to P prime. So what we can see now, or what we're going to look into now, if the point P shifted to the P prime, we want to define the change of length happening of that movement, the change of surface happening due to that movement, as well as the change of volume happening due to that. So we're going to introduce all these three parameters due to that shifted of point from P to P prime. So therefore, if you look carefully in our table here, we can see clearly this is what's like the length factor, the surface factor, and the volume factor. So that's what going to be introduced in the discussion when a point P in space shifted to P prime. Okay, so how to make it simple now? So what we have to do now, we're going to redraw this idea such that, okay, let's say we have the point P initially, let's say here. Okay, so this is the point P that we drawn earlier, and we know that you have three unit vector passing through this point P, and let's recall it. Okay, this to be unit vector x, unit vector y, unit vector z. So what I'd like to suggest now, from this simple structure, we're going to draw a box. Okay, using that as our foundation drawing. So let's draw the box now. Okay, so that's going to be what we're going to have. Okay, so that should be the box. Now, so the box is very small. Okay, so when it's small, we're going to introduce what we call it to be small increment. Okay, so let's first talk about the side of this part of the box. We know this side actually referring to x-axis. The second point, it is small. Therefore, we're going to define that to be small change according to the x-axis. Okay, for this side, since it's depending on the y-axis, we're going to define to be the small change according to the y-axis. And finally, this side of the box, we're going to define to be the small change defined by the z-axis. So if you are taking the worst case scenario, what we meant by that, if the point P now shifted to the P prime here. Okay, remember we have the 2 points in space. So one P now shifted to the P prime. We can define this to be vector. Okay, so what we are saying now, the change from P to P prime, okay, is stated as, since a vector must contain two main components, which are the magnitude as well as the direction. So I'm going to see now, if I'm going to move from P to P prime, I can choose this particular path. So this path having magnitude dx, direction of movement here, positive x. So now I'm continuing because I'm still not arriving at the destination. I'm still at this position, my final destination as P prime. So I have to continue my movement. So from this point to this point, the magnitude here is dy. So I have to add. And the direction now, as you can see in this particular, so it's positive y. And finally, I have to continue from this point until we arrive at the final destination P prime. So the magnitude dz and z prime. So that's how we define the vector movement from P to P prime. Okay, so this particular symbol, we can call it to be small change of length. Okay, vector, small change of length. So meaning that, in other words, we call it differential line length. Okay, so that's the first observation we can conclude when a point P shifted to the P prime based on the length parameter. So now we're going to go on discussing about the surface that affected by the shifted from P to P prime. So from this same diagram, what we can see is a box. And the box contains 6 surfaces. Okay, so let's label the surface. So let's call the surface on this side of the box as surface number 1. Okay, and the surface on this side of the box, we're going to label to be surface number 2. And this side, the top part of the box, we're going to label as surface number 3. So actually it must be 6 surfaces, but just not to overcrowd the diagram, I'm going to limit my labeling up to the 3rd surfaces. But actually we can write all the 6 surfaces in our diagram. Okay. So now, I'm going to ask myself now, if I want to calculate for surface number 1, so the area I'm going to define by S1, but since the structure is small, so in terms of calculus, we call it small area of the S1. So that's meaning that this area. Okay, and simple rectangular structure, this area can be defined by this side of the area multiplying with this side of the area. So in terms of mathematics, we're going to say the area actually dy dz. Okay, similarly, if we define the small change of area or small area of number 2, we can define to be dx multiplied with dz. And finally, we have the third area surface ds3 going to be dy multiplied with dx, or dx multiplied by dy. Okay, so that should be the scalar. But we can also represent area in terms of vector. So when we talk about vector, it must contain two information. First, the magnitude. Second, going to be the direction. So for surface vector, it's very simple. It still contains those two information, the magnitude and the direction. So if I want to represent now ds1 as a vector now, okay, so I'm putting arrow on top of this ds1 indicating this should be a vector. The magnitude C remain the same, the actual area, but the direction going to be the unit vector normal to that area. So from this diagram, we can see it must be x. It cannot be y or z because y and z going to be not normal to ds1 area. So therefore, in terms of mathematics, surface vector here should be ds1 in the x directions. Okay, for ds number 2, I'm sure by now you can see the logic here. So ds number 2, the direction should be y. ds number 3 is going to be z. So that's how we represent surface vector. Okay, let's ask ourselves, what happened to area number 4? And we know area number 4 in terms of continuity must be opposite to area number 1. So if I want to define now surface vector ds4, I can see is referring to the area opposite to area 1, which is at the back there. And then the area should be this length multiplied with this length. Should be still the same. dy multiplied with dz. But now the directions going to be opposed to this direction because it's coming out from the box. So I'm going to define the direction now to be negative x. Okay, so that's very crucial. And what we can see now, even though in terms of magnitude ds1 is similar to the ds4, but in terms of vector, ds1 is not equal ds4. So that should be very critical, and students must be able to see that difference clearly. Okay, so what I'm going to ask you now, if you can fill in this box yourself according to ds number 5, ds number 6. Okay, so try to fill yourself during your free time because the idea is there already for you to use, and then I'm hoping that you can get the correct results. Okay, that should be the second parameter affected when the point P shifted to P prime. So I'm going to go now to the third parameter that we discussed earlier, which is the volume. In other words, what should be the volume of the box here? Okay, so therefore what we're going to say now based on the simple mathematics we learned in our high school, the volume, the small change of volume for this box should be equal to dx multiplied with dy multiplied with the dz. So that should be the mathematical symbol that we used when we want to represent the change of volume according to which coordinate system? Cartesian. Okay, so that should be all the three main parameters affected when a point P shifted to P prime based on Cartesian coordinate system. Okay. So we have done this one. So repeating the same process now for cylindrical, because what we're going to use now, we're going to use the same step that we already create for Cartesian to define all the three parameters that we mentioned earlier based on cylindrical coordinate system. Okay, that should be our next issue that we're going to continue now. Okay, so let's make it clear now. We're going to focus on, we define it to be cylindrical coordinate system number 2 here. Okay, a point P, the same point P that we defined earlier. So meaning that we are referring to the same point. The only difference now, we change the coordinate system. Before it's Cartesian, and that point P having the parameter x, y, z. Now the same point P now represented for cylindrical. Therefore, the variable used to define that point P should be changed, given as r, phi, and z. So the same point P now changed into a variable consists of r, phi, and z. So that should be cylindrical coordinate system. So let's draw that in terms of diagram now. Okay, so that should be the one we defined earlier, x, y, z. So what we're going to have now, a cylindrical structure, because we are creating cyclical coordinate system. Okay, that should be ours. So let's make it consistent now. So just having x-axis, y, and z. So a point P is a point that we shown earlier to be located here. So that should be our point P. So let's define what should be the r now. So r should be the radius of point P. So meaning that what should be the radius of point P from the z-axis. So this is our r. Okay? That's what we define by r. And from the simple mathematics, the r should have limit. The r should be in the terms of from 0 up to infinity, meaning that r cannot have negative value. That should be the range of r. For phi, we must project the radius r so that that radius r now appear to be on the xy plane. So this should be the way we're going to define phi. Again, I would like to repeat. To define phi, we need to project the radius r to be appearing on the xy plane, and from there, from the x-axis, we're going to calculate the area until it coinciding with the shape of radius r. That should be our point phi. Okay, so now what we can say, the point phi should be in terms of range from 0 up to 2 pi. And for the z is similar to Cartesian, from minus infinity up to infinity. So that's how we define the limit or the range where the r, phi, and z can be defined. Okay, that's for the first case. So now we're going to ask ourselves, if I want to represent the point P now in vector form, so therefore we need to introduce the unit vector. Then the unit vector here, as what we have done in Cartesian, consists of x, y, z. So the unit vector now having the appearance to be r, phi, and z. So for r, the way we define the unit vector is just following the R axis, passing through the point P. So that should be our positive R directions. So that's how we define R unit vector. Okay, for the phi, now, if we observe this diagram from the top, so what we're going to have, so that should be our x-axis, y-axis, and z-axis. So the point P appears to be here. What we defined before, the R appears to be coming out from the z-axis, passing through the point P. And phi, we know that is circulating around the z-axis in this direction. So the way we define the direction of phi should be the tangential direction at that particular point P. Since the direction of angle in this direction, therefore the phi at the point P should be taken the tangential direction at point P. So therefore it's making angle 90 degrees to unit vector R. Okay, so we're going to draw here, going to be the other that. So that should be our point phi. And finally, the unit vector Z, just simply following what we have defined before in Cartesian, is showing upward. Okay, that should be how we define the unit vector R phi Z based on cylindrical coordinate system. So what we're going to do next, we're going to ask ourselves what happened when a point P shifted to P prime. But now no more Cartesian. Now we're going to talk about cylindrical. So therefore, in order for us to discuss the change of length, surface, and volume, we need to again build the reference box. So let's build the reference box here. So the box that we're going to build, going to use the unit vector as the foundation. Okay, that should be what we're going to build here. Okay, that should be the box. Okay, again, box contains 6 different surfaces. Let's label the surface now. So let's call this particular area to be area number 1. The side that we can't see, which is this side, I'm going to label to be area number 2. And the top area now, let's label to be area number 3. Okay, so what happened now? So we have defined the area. So I'm going to talk about what should be first, the length of each side of the box. Okay, so let's talk about this side of the box. So what should be the length here? We can see, so this side of the box is referring to the R. Therefore, small change of R, we're going to define to be dr. For this particular side of the box now, we are referring to the z-axis, therefore the small change is known as dz. And finally, the third side of this box going to be defined to be rd phi. Okay, rd phi. So we cannot use d phi simply because the radius actually affecting the length of that small increment. Okay, so that's why we must consider the r and multiply the change of angle to define this particular side of the box now. Okay, rd phi. So now if I'm putting this particular point here to be P prime, okay, so now mathematically I'm going to say to myself, P to P prime now, based on similar approach we defined in Cartesian. So from here I'm going to follow this path, magnitude-wise dr, and then is agree with this direction should be positive r. So I'm here now. I'm continuing my journey. So I'm following this path now. The magnitude is plus r d phi, but now the direction now in this direction, which is agreeing with this positive phi. So should be phi there. So still not arriving at the destination, which is up here. I have to continue this particular journey. So I'm going to add again. Now the magnitude of the third stage is going to be dz, z direction. So now this is what we call it to be dl. Based on which coordinate now? Cylindrical. We can see it's slightly different than the dl that we define in Cartesian. Okay, so you have to be careful then. But the steps, the concept of creating this equation still remain the same. But the only difference is the final results of these two different coordinate system. Okay, but yet what is important now for you to see in EMT subject, you have to understand the concept. Once you understand the concept, the same concept can be used in different scenarios. So don't try to solve the problem based on memorizing the step of, because if you understand the step, you're repeating the same step, so you are reducing the difficulty of solving or learning about this subject. Okay, so let's continue now. So I'm going to talk about the second parameter affected, which is the area. So the area should be three areas that we're going to define here. First, area number 1. So anyone can give a shout what should be the magnitude now. So area number 1 is referring to this particular side. Should be this length multiplied with this length. So it should be r d phi multiplying with the dz. Agreed? Okay, so let's continue. ds number 2. So anyone can want to give it a try? Okay, area number 2 should be this side, dr, multiplied with this length, dz. So it should be dr dz. And side number 3 going to be this side. Okay, should be r d phi multiplied with dr. And I can change this to be r dr d phi. You can do that. It's allowed. Okay, so that's done. So now let's define the surface vector now. So let's say I'm going to give the direction now. So the direction must be normal to the area. So for surface number 1, normal going to be r. Surface vector number 2, the normal should be phi. Surface vector number 3, the normal should be z. Okay, similarly, if you want to define ds number 4, and we know ds number 4 is opposite to area number 1, so we have the same magnitude, but the direction now opposing to the r positive. So now what we have now, r d phi dz, but in negative r directions. Okay, hope you're clear with that. And for the volume, the third parameter dv, simply the area, sorry, the volume of this valve should be this side, the length, multiplied with this length, multiplied with this length. So what we should have now, r dr d phi dz. So with that, we can fill all the empty space in this table according to the cylindrical coordinate. So I'm going to leave to you all to define the same parameter, but in the different coordinates. Is the last coordinate system that we mentioned, the spherical. So please follow the same procedure that we already seen earlier when we talk about Cartesian and cylindrical. So repeat the same process so that you'll be able to fill in this gap or this blank space yourself. With that, I'd like to thank you for your attention given. Inshallah, we're going to see you again next time. Assalamu alaikum wa rahmatullahi wa barakatuh.